Okay, time to start. Networks are like onions. I should put Shrek on my slide, but yeah, I prefer to put some networks if we talk about networks. So I'll be talking today to you about TensorFlow, and I was asked to make it interactive, but then I thought 35 minutes, it's not enough time to make it very interactive, so I have a surprise for you. I will show you a few demos. If you look at the bottom of the slide, there is a platform. You can go and have the whole environment run the code I will be showing to you. So you can just go there and then run it at home. But because we only have 35 minutes, yeah, I'll prepare to show you some stuff, and then you can try it all at home. So who am I to talk to you about TensorFlow? Well, I do stuff with data. I do stuff with deep learning, with machine learning, with data mining. I work at Microsoft for another 2 weeks. Not sure what to do next. Probably take some vacation time. But at the moment, I'm a data solution architect, and what I do in my daily job is I have sets of accounts aligned to me, and I try to solve their problems with the cloud, which is Azure in my case, with machine learning, with databases, but also data in general, with providing the insight from what they have, what they gather. So if you want to tweet me, this is my Twitter handler, but basically I'm the only person in the whole world named like this, so wherever you find me, that's probably me. So what are we going to talk to today? The theme of today is layers, right? Onions have layers, and why layers? Probably because networks have layers, and I will talk a little bit about this. I will talk a little bit about what is deep learning, but then I would just like to go straight to the code, straight to the example, and show you how to build your network using TensorFlow, going from one layer to 5 or even more. We can have a discussion later how many layers did I create. So let's start. Who here works with deep learning in their daily jobs? Quite a few people. Who uses TensorFlow in their daily job? Who came here because TensorFlow is this new cool thing? Yes, that's the thing. So yeah, what is deep learning? And yeah, because I know you work with deep learning, you need to now answer my question. If I ask you, what is deep learning? What would you say? You guys at the front are screwed. Yeah? Come on.
It's a neural net with lots of layers.
Neural networks with lots of layers. Very good. I gave you a hint with my title, right? Yeah, anyone else? So my favorite, yeah?
Learning features from a data set that might not be a number or text.
So learning features from the data set that might not be numbers or text. Anyone else?
Learning deeply.
Sorry?
Learning
deeply. Learning deeply. Yeah, what is this deepness?
More than one hidden layer.
More than one layer, right? Because those layers are the key. So my favorite definition of what deep learning is matrix multiplication, and like a lot of matrix multiplication and some adding of them. So I think deep learning is a game changer, and I'm guessing because you're here, you're thinking similarly. Now we are living in the future. We are living in times when computers are doing stuff that look like magic. They still don't think, they still don't have a consciousness. So even if the headlines is telling you that this is deep learning, this is AI, and robots are getting consciousness, you probably know we're nowhere near yet. So if we think of those neural networks that we were talking about, we usually think of artificial neural networks, but they were built based on the real ones. Apart from the fact that there are neurons and there are some kind of layers and there are some kind of connectors between those neurons, there is absolutely nothing more in common. Or maybe I should put it differently. We have no idea how human brain works. We know some of the stuff, some of the elements, and we're trying to mimic the brain. And like 10 years ago, if you were in an AI industry, if you were, well, I can see from some of the people, if you were adult that at that time, people were saying that neural networks are actually a very niche thing, because it's someone that took how the human brain worked and just put it in some mathematical stuff, and it's very interesting, but no one will use it in production for anything useful. 10 years after, and yeah, we have our neural networks that are doing a lot of stuff. But what's underneath? Who knows what's underneath when we talk about neural networks? Who knows the mathematics? Don't be shy. I've seen more people working with deep learning. So who understands this? Maybe. Yes, see? So if you don't understand this, you really should pick up if you want to really understand how deep networks work. But because we have a lot of tools, a lot of APIs, a lot of black boxes at the moment, it's probably not crucial, but I still encourage you to understand that. So, very briefly, if you see those columns of those circles, the circles are neurons, the columns are layers, and layers are just group of neurons that have the same, I would say, parameters, capabilities, something in common. And we group them for a reason, because if you group them and if you put all the mathematical equations together, you don't have to do all the for loops that previously people were trying to do with neural networks, and that's because they became a niche technique and no one actually used it. And then if you put it together, you have matrix multiplication I was talking about. So it looks like neurons if you try to visualize it, but it looks nothing like neurons, nothing like layers when you try to write the code, at least when you try the mathematics that is behind it. So how does it work? Every neuron has something that gathers the inputs from the previous layers. It could be all the inputs from the previous layers, it could be a little bit less or something even additional. And then we try to multiply the inputs by some wages, and then we aggregate it somehow. The simplest thing would be the sum. And then the result we put through the activation layer. And sometimes we even have the threshold. If the output of this activation layer is below the threshold, we're putting the signal through. If it doesn't, we don't. So that sounds very simple. So what's so difficult about those neural networks? Because every introductory course is simple. If you go little bit more advanced and work with more advanced stuff, it's not that simple anymore. That's why we have PhD people that work on actual mathematics behind it, that build libraries like TensorFlow. And just to remind you, again, not TensorFlow, neural networks are not a new subject. If you look back in history, they go back into 40s. That's quite a long time. 60, 70 years, almost 80, that people started working on neural networks. What has changed? Why neural networks now? It's the fact that we now live in the future. We have a lot of data, and we can store those data. We have the capabilities of storing them, of performing them, of performing computations on them. We have stuff like GPUs, TPUs, and probably other use that people will figure out in the near future. And people are actually working on, you know what? Matrix multiplication to make it quicker. And then there are tools like TensorFlow that make it accessible to basically everybody. Nowadays, actually, you don't need to understand what's underneath. If you understand the concept of layer, if you understand the concept that we have input layer, output layer, something in between, you can use TensorFlow almost seamlessly. But I'll just put my opinion, my strong opinion here. Please understand what's underneath. Understand what your algorithm is doing. Use the black boxes, but learn what's behind it, because it will give you some numbers. And if you don't know which numbers are there and how to transform them into useful insight, it's just a number and doesn't mean anything. And the last thing before I will show you the example is great talk on TED that was, you can see how many views were there, and I think I took the screenshot a month ago, it should be much more. This lady was talking about a deep learning project. She didn't call it deep learning, but you could kind of guess about how we as humans and how like 3-year-old kids are learning to recognize images, and how they took this kind of thinking and applied this thinking into the machine and created the algorithm that could recognize what's on a picture. And she started it very funnily with pictures of cat. So if you don't know what deep learning is or machine learning is, because the concept is the same, it's like try to explain to somebody the rules that would describe there is a cat on this picture. You probably will miserably fail, and people did fail for years with this task. It was like the most complicated task in machine learning, until we found a way of actually putting a lot of data into the algorithm and just saying, you know, algorithm, learn based on those data. And the algorithm didn't go through figuring out how to explain a cat to a person. It just worked kind of like we think children are learning. Looking at a lot of pictures and kind of automatically doing these connections with labels. If a kid is going through the park with his mom and she's showing them a squirrel or a cat or a dog, there is some kind of a process of learning from images. So please watch this amazing talk. I think it's brilliant. So let's start with the example. It is a simple example, and you can find pieces of the code I will be showing you on the TensorFlow pages. The reason I picked up a simple example is I can show you how the algorithm works from the start to the end in 35 minutes with 5 or more layers. So if you don't know the data set, it's a very famous data set and like a hello world data set for deep learning. There is a data set of digits that people handwritten. And the task is to train the network and have the network trained so it can label the image of a new example, assigning a digit to it. Don't be fooled, those are labels. I know they look like numbers, but those are labels. This is a classification task. This is not a regression task. So those images are of the size 28 by 28. So to begin with our network, we will flatten it. And actually, TensorFlow is giving you the possibility of flattening it just out of the box. If you read the NIST data set, it will be flattened by default. So what do we do next? Once we have our data set of our flattened files from the training data set, there is a classification process that is training, classification process that is training the network. So it takes batches of those images and try to learn some weights. So which weights are we trying to learn? So I will just go back maybe to this thing, and you can see there are some weights here. There could be also a bias there. So all those parameters will determine how good our network is after it's trained, because once we have those weights put together properly, our network will be able to classify the new examples. So all the process of classification of any machine learning process is to tune some weights, some parameters, some coefficients. And because we have a very simple network, our parameters are W and B. So this is like the simplest neurons you can imagine. We only have two layers. There is only an input layer that I'm putting the images through that are flattened. The input layer size is of the size of the flattened file. So input is basically, it is called input layer, but like in my mind, I don't treat it as a layer because it's basically the data that you're putting through. But yeah, if you want, you can also treat it as another layer. So for me, this network has one layer, only the output one. The output layer has only 10 neurons. Why 10? Because we are trying to classify, to assign a label that is a digit. And we only have 10 digits, right? From 0 to 9. So what is going on in this network is we're getting the input. The input is from the 0 to 1. So this is a grayscale input. There are no colors in this data set. So it's normalized, etc. So if it's 0, it's white. If it's 1, it's black, or the other way around. I never remember it. So we're putting it through, and every neuron from the input layer is connected to every neuron to the output layer. So yeah, a lot of connections. So 7,840 connections. So it's starting to be complicated, but not yet. What is happening next is we are getting usually a softmax function or something else, but we're getting the label of the neuron that the output was the biggest. And this is our label. This is what networks is deciding to do to classify our example. So we're hoping that for this handwritten digit, the 9th neuron of the output layer will be lit up as the best one, and this is the answer of our network. So let's go through the demo. And as I said, you can just do it later and try to do it what I'm showing you. So this is my profile, and I created a scenario for you. This platform is an interactive learning platform, and I just happened to create a scenario for you just for this talk that will go with the demos to create layers. So everything I'm saying, like everything that is important that I'm saying, will be here, so you can read it later if you don't remember. So we are reading the MNIST data set, and let's create a layer. So I will show you some helper functions. So I have 4 functions. First one is just to read the data. It's called read MNIST. Oh, I don't know if I can. Yeah. The second one is just trying to build a loss function. So it's basically using softmax cross entropy with logits, and then I'm using Adam optimizer. You can try to use gradient descent if you like. I just found it with more layers that Adam is working much better. Then I'm just trying to calculate accuracy. So how good my algorithm is. If you know something about TensorFlow, you will know what I will just say, but for those people that TensorFlow is new to them, is I'm creating an algorithm. I'm creating the architecture at the moment. I'm not running any code. Even if I run this function, it's just creating what is called an execution graph. So TensorFlow works in a way that it has the delayed execution. So first you're saying, build me the equations, build me the thing in this way, and then run it. How do you run it? There are a few ways. I'm using the eval function. So how do I run it? Then I run my session. First you need to create an interactive session, then you need to initialize all the variables, and then I'm running my algorithm several times. This is a hyperparameter for your machine learning, deep learning algorithm. And then I'm trying to learn, which is here, accuracy eval, on a batch. So I'm not using the whole training set, I'm using just pieces of it. So I'm using batches. This is proven to be very effective with deep learning. Just to take batches and the weights, the parameters, the coefficients of your network will tune better. So this is where I'm trying to get the accuracy, and this is where I'm running my training step. So I'm only evaluating my accuracy once in every 100 steps, because I'm running this learning process, this training process, 1,000 times. Then I'm trying, how do my network actually perform in my test and validation data? So let's see how our very simple dense layer, this one, look like. So if we look at the code, I'm just reading my MNIST data, and I have two placeholders. One is for my training data, and one is for my labels. And I only have one layer, which is called dense layer. This is where I'm running my first function, and this is when I'm training and testing model. So this is when I'm building the training model, this is when I'm actually running it. And those two last steps and those first steps will not change regardless of how many layers I will add. That's how I structured my code. So let's just focus on this thing. This is just one layer. I told you input layer is not a layer. Even TensorFlow is not treating it as a layer. It's treating it as a placeholder. Placeholder is a structure in TensorFlow. When you're actually running your network, you're putting the data into it. It can be anything, but very often labels and actual training data are used with placeholders. So TF is the short from TensorFlow, which I imported at the beginning, as you can see. Has this namespace of layers, and you have plenty of layers there. If you want to just use a simple one, you just use dense, but I will show you more complicated layers. And you can see it's very, very simple. I only am saying use those inputs, and this is the label size. This is the size of our output layer. Label size is 10 because we have 10 digits. So let's run it. So it's downloading my data and putting it into the folder. So it was pretty quick because it's a very simple one-layer network. And you know, this accuracy, not great. If you use stochastic gradient descent, it will be better, but stochastic gradient descent won't perform very well if you have more layers. So maybe we should spice some stuff a little bit more.
Excuse me.
Yeah?
May I?
Of course.
Do you always have to use the labels, or you are doing some unsupervised learning?
If you're doing unsupervised learning, that's the definition. You don't have labels. But if you're doing classification problem is supervised learning.
Okay, but in the placeholder you can.
Yeah, then you're choosing. Your placeholder is just a data that you will pass through when you're running something. It doesn't even have to be training, but it's like a data that you put into the whole architecture you just created. So let us put there another layer, which is called hidden layer. Why is it hidden? Because it's between input and output. I remember from my school days, we were trying to explain to us why it's hidden, why someone called it hidden, even though we all can touch it and see it. It's just in between, but in between layer probably wouldn't fly, so that's why the name. So we'll add another layer, which will be dense, but we'll put an activation function after that. And there are also few theories why ReLU, because this is what we will be using, the ReLU. I don't recall how you should pronounce it, probably ReLU. We will use this function, and this is this red one. So it has 0 when the value is less than 0, and it's linear when the value is bigger than 0. So instead of using like sigmoid or tan, where they have a limit in like 1, when you're actually training your network, and watch out because this is the moment when you need to go deep down to understand stuff and maths, there is a derivative taken at some point to find out which way you're moving to the global maximum or minimum, and this is like we're trying to minimize loss function. So, for example, sigmoid derivative would just be stable, and this is like, or we would just go to like a line which derivative will be 0, and this is called vanishing gradient problem. So ReLU is supposed to fix this problem. So we have actual derivative, we actually have a direction that we should move when we're training our network. The truth is, just worked better. So people just tested all of those functions, and ReLU is just working better, gives better results. So this is a very popular function when you're adding hidden layer. It doesn't work for everything, but for MNIST it does. So what we are doing is we're adding another column, our hidden layer. And instead of just having our matrix multiplication with weights and bias, we're also putting an activation function around it. So the math is very simple. Those are matrices, and there is a function put through it, and then we're just putting it through the output layer. The math, again, behind this, no networks, no layers, but it kind of creates this nice mind picture. So how to create a hidden layer with ReLU in the TensorFlow. So if I go for another layer, there is my code that I called dense ReLU, and maybe too much. And I added only one Morse variable, which is hidden size, 1024, so the number of neurons in the hidden layer. And I had added another layer. Everything else is kind of the same, except that I added another layer where I put as an input our input, and I've connected my hidden layer to the output layer instead of like it was previously. Previously I connected with the input. So now input, it goes to the hidden one, and hidden one goes to the output. So very nice connection, and TensorFlow makes it very easy. And you can see that I have this parameter now. I didn't have it here, right? I have it now. I'm saying like you don't just multiply and do your stuff with weights and biases, but you also put a ReLU function at the end. So let's run it. And it should run a little bit slower because we have another layer, and it should take more time. Still quite okay. And the accuracy is much better, right? Still not amazing, but much better. But you also need to think that I only have 1000 iterations. Maybe if you change the number of iterations, it will learn better, maybe not. Maybe we should add another layer. So Maniz's data set is a bunch of pictures, and we did a silly thing at the beginning. I mean, I did the silly thing at the beginning that doesn't take advantage of this 2D picture. What did I do? I flattened the files. So there's this thing called convolutional neural networks, or convolutional layer, that that is advertised as the layer that will allow you to keep less weights, less parameters, less coefficients. Because if you think adding dense layers will produce a lot of connections between neurons. And if you calculate how many weights you need to keep and train and tune and adjust, it just takes a lot of time. So convolutional neural layers are supposed to keep them, like a little bit less of them. And that's true, but for me, it's also the thing that allows you to see the region of your picture. So you can see at this picture, it just takes the region of it, does all this matrix multiplication, but then just moves on to another region while keeping the same weights. And the beautiful thing is that it just takes the context, and you can adjust this context. You can put how far it can jump in one step and how big your kernel, your filter is. It does another thing, which is a hyperparameter of this convolutional layer. It adds depth. So there is another dimension that it does. So this is something that you set up. You can set it up as 1, but you can set it up as 70. But this will also increase the number of parameters you have to tune, so you need to be quite well, conscious about this. What did you want to achieve? Did you want to achieve smaller number of parameters, or did you want to achieve looking at the regions and take advantage from it? There is another technique that is called polling, which does the similar stuff, but doesn't have parameter. Actually, it doesn't do the similar stuff, it just works similar way. It also goes from region to region, but only performs calculations, only performs like an aggregation, like average, or taking the maximum value. So you could see on the picture that max polling from the first square is taking the maximum value from those 4 numbers. So it's a very simple context, but it does not hold any weights, any biases. This layer doesn't need tuning. It's just some computation. So this is my thing. Is this a layer, or is not a layer? Or is this just some calculation that you're performing? So if you look at TensorFlow, it is in the layer namespace, but, well, I would just put it to your judgment. So our network looks like this now. We need to put the input layer in 2D again. Then we have convolutional network, or 2 of them, depending how you treat it on the pretty picture. I'm very good, right, with my PowerPoint presentation skills. So then we have convolution plus max polling. I put max polling, and then we have our, at the end we have our output layer and the hidden layer. The layer in the middle is the flattened thing that comes out from the max polling layer, because the hidden layer needs something that is flat again. So we need to sometimes do all those stuff, flattening and deflattening, back and forth. So let me show you how the code looks like now. And I'll go here. So the code didn't change that much. I just had to reshape the image. So I'm taking my X input and I'm reshaping it into the 28 by 28. So now we have a 2D input, and I've put it as X image. So this is what I'm feeding my convolutional layer now. So this is TensorFlow layers convolution 2D, because we have a 2D thing, and I've put as an input X image. I've put 32 filters, so the depth is 32, and the kernel size of 5 on 5. The padding same means that the output of this layer will be the same size as the input. Because if you imagine that we have more padding, we could increase even our output size. And as an activation function, we again use ReLU. What I'm doing next is adding another layer, or not a layer, but it's called a layer in TensorFlow, which is max polling. And I'm just saying, takes max polling from this convolution layer and pole size, so the square size is 2 by 2, and skip by 2, and takes the max. If I put average polling, it would take an average. So then I need to reshape my output from my polling layer, and then I'm feeding it into the hidden layer. And if we run this code, it should slow down significantly. So we have few other layers. It's not bad. It's quite a nice hardware behind this, but still, it's not just like it was. Why? I know I told you a layer, but why is it slowing down the whole process, any layer? Significantly, because of course it's slowing down on computation, it's slowing down the process. Because we have another layer of weights and biases that we need to tune. So all this training thing is going through the gradient descent or gradient of some kind and trying to calculate the derivatives, well, maybe not the derivatives because we have backward propagation, but all of the stuff. And again, step end of training. So this is becoming better, 97%. So if you try, by the way, with just one output layer and using stochastic gradient descent, this is the accuracy you would get. If using Adam, you see the better accuracy with more layers and with more iterations. Again, we only have 1,000. So if we add another layer, which is, I'll just show you that, like here. Another convolutional layer and another max polling. Well, another set of weights, and this will be very, very slow. But you know, it's quite easy to think of it. That's why people think in layers. So let's see how does it look like. Again, too much. So we have one convolutional layer, another convolutional layer, dense with ReLU and dense. So first convolutional layer, it's the same one that we had before. And now we don't have to flatten it because another convolutional layer is taking 2D stuff. So we're feeding our first polling layer into the second convolutional layer. And then again, we're doing max polling. And then we reshape it, flattening it, and putting it as an input to the hidden layer, and then hidden layer is going through the output. Let's run it, and I will just go back to my slide because this will be much, much slower, just to show you. Yeah, I'm bored now, okay. It will run. So I was talking to you about how you can tweak the algorithm using different optimization algorithm, or probably different learning rate or number of steps. And all those stuff are the essence of what machine learning is. Not just the classical machine learning AI in general. Because we want our algorithm to work for the new data. So there is this problem called overfitting, and it's something that beginners don't notice, even though it's in every introductory course to data science or to machine learning. It's because you're trying to learn your algorithm and it's performing better and better. You could have seen all those one per step logging there, that the performance was great. Sometimes probably there was 1, so 100% it was performing perfectly. But it was performing perfectly on training data and only on the batch that was currently in process. So not on the whole data. And the fact that it was only performing great on the training data is connected with overfitting. Overfitting is the thing that happens when we fit our training data perfectly, but it's not very good. It does not generalize for the new data. So that's why I'm at the end showing you the validation and the training and the testing set accuracy, because those are the data that this algorithm hasn't seen, so it didn't learn it by heart. So there is this technique called dropout that is supposed to fix this problem of overfitting. So I think someone had a stroke of genius while drinking a beer and sitting in a pub and thinking like, you know, it's too good. It's learning those data too well and does not generalize. Why don't we just shoot all those neurons like randomly? Just don't take them into account. And it's a very simple technique. It's actually shooting down all those neurons and just not pass them through. You're just putting as a parameter the probability of should this neuron be dropped out, and that's it. That's the whole dropout layer. Again, layer or not layer depends how you treat it, because again, it does not hold any parameters except this probability thing, which is just one number, so basically no parameters, and just perform some calculations. So the network looks like this now. I kind of said there will be 5 layers, but again, depending how you treat them. So dropout is just shooting down some of the neurons. So I've put the dropout after the hidden layer, after the ReLU. And let's see how does this work. Hopefully the algorithm, see? If you put like 20,000 iterations on the just convolution without dropout, it should go to 99.5, something like this. But this is just 1,000 and took like 5 minutes. 20,000 should take around half an hour. So let's see the dropout. So we have another placeholder. That's what you were asking for. This placeholder is only holding the Boolean value. Should we put dropout in our network? Why shouldn't we?
Test.
So think of it like we have you're right, testing phase. So think of it in this way. If you're training the layer, you're randomly shooting down the neurons. But once you have every weight there and you want to just use it to classify new examples, you want all the neurons with all the weights. You don't want them now randomly shut down, right? Because your algorithm now is becoming, first no good and then not deterministic. So in the training phase, we want to drop them out. But in the testing phase, when we're actually using it, everything should stay as it was. So I have the placeholder called should drop, and I have another layer that is called dropout. And again, TensorFlow layers dropout. So I'm just saying, get the hidden layer, this is the rate which you should drop all the neurons, and take this parameter, should it drop or should it not. So if you put 0, you shouldn't drop, or if you put false, you shouldn't drop. It will just, it would be like this layer doesn't exist. So if you go to this, let me just go back. sorry. If you go to our training phase, I have another attribute that I'm passing through. And if you look at the help code, there is the code that now, when it's training stuff, it's saying you shouldn't drop out. When it's testing stuff, it says you shouldn't drop out, but when it's training and used in a train step, this says it should drop out. Why do I have you shouldn't drop out here? Because I'm showing you the accuracy on the batch when I'm training the data, and I want it to be an actual accuracy, not the random thing that is currently in my network. Okay, that's the last code, and I will just leave it, and we go to the summary and we drink some more beers. So this will be basically something that with 1,000 iterations won't bring anything to the picture in terms of accuracy, but with more complex, bigger networks, it is really making the difference. And you can see that the speed is similar to what it was, because dropout is not that time consuming. Much more consuming is this tuning all those weights. So let me go back to the summary. So I talked a little bit what deep learning is, and we went to the classification task of getting handwritten digits and classifying them, labeling them with the digits, actual digits. We went through 4 demos. In this our output layer, I give you as metaphysical questions which are the layers, which are not, but really encourage you to try out Katacoda if you want to go through this process, or just take the code that is there. If you go through my GitHub repositories, the actual files of the TensorFlow are there, but if you don't want to use your computer power, just want to try out the code, go there. It's free. You can use it and learn many stuff. Also, if you want to contact with me, as I said, any combination of my name and my second and my last name, it probably will work. So I encourage you to do it. So thank you very much.
What are the limitations of TensorFlow according to your experience?
Sorry?
Limitation.
If you look at the metrics that some third-party companies are doing, TensorFlow very often comes not like as the fastest one. But I spoke to many people that are using it in production, and they said it's not that crucial, because we now have cloud computing, and you just put it to learn for several hours, and if it takes you 1 day or 3 days, I mean, like 1 hour or 3 hours, it doesn't really matters that much. If it matters, this would be a limitation. To tell you the truth, the new version of TensorFlow just came up, and I upgraded this environment to the newest one, and it just fixed all of the problems I had. I had segmentation fault problems with just 5 layers. I had, what else was there? Oh, when the test set was too big and memory was too small, it just didn't didn't evaluate my test set because it was too big. I had to partition it, but it is getting better because the community is huge, and people are just putting the problems out there, and they are getting fixed. So last time I checked, it's like 2 days until you're like putting a question or like pull requests, and it just there is a reaction on it. So I think it is getting better, but yeah, I think the speed would be the biggest one.
But to
two-part question. First is, if I expand the width of any given layer, so as a child, right, every time I show him a new feature of a cat, he doesn't really start again from scratch and we're going to optimize all these layers.
Right.
So do we have ways to kind of use whatever we already learned when we can expand or deepen the network?
We have ways, yes, of course. It's called like incremental learning, right? But if you used this classical neural network, you would need to retrain it from scratch. But yes, deep learning and TensorFlow have the features to do it.
And because we use this deep network, that means essentially it becomes more and more like a black box. So then how do we, because it seems that the model predictive power becomes quite vulnerable to the kind of data you feed it in. So if you did have some certain issues and it just kind of propagates through because you don't have visibility in the middle to correct it. So then is there any kind of standard method to make sure that it will feed into this predictive power at the end?
I don't think it's a problem of depth. The question was if, because we have so many layers and the architecture becomes more complex, so it's not explainable to the people, and such a small thing as bad data could be propagated and spoil our computer. It's the problem for all machine learning algorithms, actually. If you have big data, if you have bad data, they can spoil your algorithm. The question is how much of the bad data you have, and the visibility. You can see a lot of examples how people are seeing, like how the image is processed. So there are techniques to see, like in the middle, how does it work? What's the output at this layer? That's what I said with the hidden layers. They're not really hidden. At any time, you can take this hidden thing that I've built and evaluate it and see what's on the output. So you don't have to just look at the end. You can look in the middle. You have the access.
How do you know when it's time to add another dense layer or convolutional layer or max poly? What's the strategy to choose next layer?
Which layer to choose for which problem? So people are doing research, so start with what they are doing, but then I would say try it out and see how does it work. And again, we have cloud, we have cheap computing, and our computers, home computers, are quite powerful. Even if you want to use GPU, you can use GPU. Run different experiments and see what works best. But that's the thing with machine learning in general. That's the actual what it is. For you to experiment, apply the scientific method, hence it's called science, and you know, convince yourself and convince others that this is the result. Yeah.
So I understand you develop systems with Microsoft. Do you use CNTK at any point, or do you also prefer to use TensorFlow?
So I would say TensorFlow won the popularity contest. I was raised in a tradition that CNTK is better, and especially when it comes to the speed, which I talked about. But for me, it's more like a tool, and because CNTK is open source, but probably is only evolved within Microsoft. And even if you have a pull request, you're allowed to only do small changes. If you want a big change, you should raise an issue. It's a different type of collaboration around CNTK. So even if there are shortcomings of TensorFlow, I believe they will be fixed by the community. Anyone else?
One more question. How do you record the hyperparameters for your tests? Because you probably try the configuration of the network, of the amount of the epochs, what else?
Right, so simplest way is some configuration files. So you have some networks and you just feed the configuration files and you get those parameters. But you can also do it by hand. You can have even a big CI/CD pipeline that just runs the network, the same network with different stuff, and tests which performs better. I'm not sure. I probably should know that, but I'm not sure if there are automatical TensorFlow tuning libraries or tuning phases. Maybe. So the idea is to just try out few things or all the combinations of things and just give the final answer based on something like accuracy, right? Yeah?
How effective is dropout at kind of preventing overfitting, or other techniques that can be more effective in that?
So I probably would look it up how it is effective in comparison. It is not effective with NIST. I was just showing you this as an example. It's not a complicated network, even though it has 5 layers. It's not a big network, and we only had this data set is pretty simple. It's basically zeros and ones, even if there is a spectrum in between. So for NIST, it's not effective. I would just say it's like with every other technique. You just try it out and see how does it work. I think something else would work better with NIST, which would be, kill me now. Regularization would work better with NIST than dropout. But it all depends on what other hyperparameters and what other configurations you have. And where do you apply the regularization? Do you apply it to all of the hidden layers or the weights, or just weights, biases, etc.? So yeah, it's just like amount of those calculations is growing quite rapidly.